Hi everyone, I am Jiajun Gong. I am from the Hong Kong University of Science and Technology. It is my pleasure to talk to you today about our work, Surakav, generating realistic traces for a strong website fingerprinting defense. This is a joint work with Wuqi Zhang and my supervisors Charles Zhang and Wang. More and more people have been turning to privacy-enhancing communication tools like Tor to access the internet. However, a local eavesdropper can launch a traffic analysis attack known as website fingerprinting to de-anonymize the user. In nature, it is a classification problem where the attacker uses a machine learning or deep learning technique to infer the web pages by timing and size information in the packet sequences. Modern attacks have achieved more than 90% prediction accuracy, posing a great threat. To address this problem, several defenses have been proposed. For example, lightweight defenses such as WTF pad and front rely on the randomness of the way they inject dummy packets. They do not delay user packets, so they incur low overhead. However, they do not provide strong protection against deep learning attacks. By contrast, walkie-talkie and Tamro force users to load pages in some predefined patterns. They are effective but hard to implement. We try to look deeper into the designs of those effective defenses and identify their problems. We find that Tamro forces packets to be sent at a constant rate, totally ignoring the characteristics of loading different pages, leading to large overhead. While walkie-talkie reduces the overhead by choosing a suitable sending pattern for each page, it assumes that we can know the pattern of the web pages in advance, which is hard to achieve in reality. To fix these problems while holding the defense effectiveness, we come up with the idea of using a generative model to generate diverse sending patterns for us. Therefore, we propose a new defense called Surakav. The general idea is to leverage a generative model that learns a variety of sending patterns to guide the packet sending process. Under the defense of Surakav, even if you load the same page several times, the data will be tunneled by different sending patterns, which greatly lowers the attacker's success rate. To achieve our goal, we first need to train a generator. There are two issues we need to consider. The first is, what pattern should we mimic? We decide to directly learn from the birth sequences of loading real web pages. The intuition behind this is the sending patterns should capture the general characteristics of a normal page load, so that following these patterns won't incur much unnecessary overhead. And there are already a few large datasets from previous studies that can be used as the training source. The second question is, what generative model should we use? We choose to use a generative adversarial network, namely GAN, as it was shown to be able to generate realistic traces with more diversity in our preliminary experiments. Since there is no ready model for our task, we built the GAN from scratch. First, we have a generator, which is a multi-layer perceptron to generate fake traces. The input is a label of a web page and random noise. It tries to generate a trace of this page. Then, both real and fake traces will be fed into the discriminator. The discriminator is asked to tell them apart by answering whether the trace is real or fake. This feedback will then be passed back to the generator to improve its ability to craft realistic traces. However, since network traces are complicated, we further introduce a novel observer to refine trace crafting. The observer is a pre-trained website fingerprinting model. For those fake traces that successfully fool the discriminator, we further query the observer to see whether they are classified into the expected class. Then, the observer will give this feedback to the generator. So the final training loss is the linear combination of the feedback from both the discriminator and the observer. We introduce a parameter alpha here to balance these two losses. After this adversarial training process, we can get a generator that can output realistic traces. We choose to use Rimmer's dataset to train the model, as it is one of the largest existing datasets. We randomly pick 100 classes. For each class, we pick 1000 instances. We use Warsaw staying distance to monitor the training process. Warsaw staying distance is helpful in estimating the distance between two probability distributions. In our case, we try to make the distribution of fake traces as close to the distribution of real traces as possible. We find that after the training, the Warsaw staying distance is reduced from 0.9 to 0.02. To visualize this change, we plot the mean burst sizes of the generated traces of the same class. As shown in this figure, we use a positive number to represent an outgoing burst and a negative number to represent an incoming burst. After one epoch, the fake trace is different from the real one. But after 500 epochs, the fake traces are statistically close to the real ones, as the red line is close to the black line. Last but not least, we find that 90% of the generated traces are classified into their expected classes. After we obtain the generator, we can start to send packets based on it. We first generate a trace T, then the client and the proxy will take turns sending bursts based on T. The client controls the timing. The time gaps are randomly sampled from a distribution. We learn such a distribution from real datasets using kernel density estimation. By using random time gaps, we can leak as little time information as possible. Meanwhile, we guarantee these time gaps follow the general loading pattern. However, we do not strictly follow the sending patterns, as this strategy may lead to high overhead, just like the previous defense does. Therefore, we propose two mechanisms that dynamically adjust the sending patterns in real time. The first mechanism is burst size adjustment. We introduce a parameter delta here and compute two boundary values given a required burst size B fake. Then, at the sending time, if the size of the buffered data is lower than the lower bound value, we will adjust the burst size to the lower bound with some dummy packets. Similarly, if the size of buffered data is larger than the upper bound, we will hold some real data and only send a burst of upper bound size. If the burst size is within the range of delta, in other words, is close to the required fake burst, we will directly send out this burst without modification. A smaller delta will respect the required sending pattern more than the real pattern, and vice versa. By taking both patterns into consideration, such a mechanism provides more flexibility for users with different security preferences. To further reduce the data overhead, we introduce another mechanism called random response. We allow the proxy to skip sending a total fake burst when there is no real data in the buffer with a 50% chance. We only apply this mechanism on the proxy side because we usually have much larger bursts on the proxy side, which mainly contributes to the final data overhead. To evaluate our defense, we consider the open world setting, where the attacker monitors a list of 100 web pages. The client may also visit other 60,000 pages. All those pages are from the Tranquil list collected in January 2021. The attacker's goal is to find out whether the client is visiting any monitored page and which is it. As simulation could be inaccurate, we decide to implement each defense and directly measure their performance in the real Tor network. To achieve that, we implement each defense as pluggable transport. In this case, the entry node will be our cooperating proxy to help forward real packets and deal with dummy packets. The data from the Tor process will be reshaped according to the defense protocol before they are sent onto the connection. We rent several servers on Azure. We place the user in Hong Kong and the entry node in the US to create some physical distance. We first show the performance of Surakav against different attacks. we present Surakav at two overhead levels by adjusting the parameter delta to 0.4 and 0.6 respectively. As a baseline, all the attacks can achieve over 90% accuracy on the undefended dataset. As shown in this figure, Surakav is very effective against KFP and QMU, even under the lightweight setting. For stronger attacks like DF and TikTok, Surakav is rather effective under the heavyweight setting. Next, we compare Surakav with other defenses against the strongest attack TikTok. As we can see, Surakav Heavy has the best performance among all the defenses. It reduces the true positive rate of the attacker from 97% to only 6%. Surakav Light, on the other hand, achieves a similar protection level as Front, reducing the true positive rate of the attacker by nearly 60%. When it comes to the overhead, we find that, compared to Front, Surakav saves 42% data overhead to achieve a similar protection rate, or offers much more robust protection at a similar overhead level. When we compare Surakav to Tamro, which was considered the strongest defense before, we find that Surakav requires 40% less data overhead and 10% less time overhead to achieve an even lower true positive rate. Modern defense evaluation also includes the information leakage analysis, which examines the amount of information an attacker can learn from a specific feature. We conduct the same analysis using the WEFDE framework and plot the cumulative distribution function of the information leakage for the top 100 informative features. We find that Surakav leaks the least bits of information for these features among all the defenses. Last but not least, since our defense utilizes a generator, we also care about its distribution cost. Suppose the top directory servers are responsible for distributing the trained model. According to our estimation, it only adds 1 to 8% extra bandwidth overhead to the existing bandwidth consumption, depending on how frequently and how many users will update the model. To sum up, in this study, we propose a strong website fingerprinting defense called Surakav. Surakav leverages a self-designed generative adversarial model to generate realistic sending patterns. It tunnels real data through these patterns, while also applying two mechanisms to bring about more randomness and to reduce the overhead. If you are interested in our project, you can find the GitHub. Thanks for listening to this talk.
Speaker.
Hi.
Questions? No questions. Okay, so is he online?
Yes, I am.
Okay, sorry. Good. So I have one question. Actually, not my area. Great talk, actually. Very interesting. But I was wondering, so you train actually your GAN on the data set that was collected in 2017. So is this something that needs to be retrained? Is it something that affects in some way, you know, the packets you generate, or is, I don't know, did you try?
Since we don't, actually we trained on two different data sets, which is Rimmer's data set and another is Suraname's data set. And I think they show similar performance. And also we try to use, for example, the first 100, not the first, randomly choose 100 classes in Rimmer's dataset, and or choose like 500 classes in the dataset and try the performance. And they perform like the results are similar. So I guess maybe it will have like minor effect on the defense performance, but it is possible that it could affect the performance in some way if you know, the collection year is too far away from the year when you test the defense. But we don't test that. Like, we don't have existing datasets that have such long time gap. Yeah, we explore some possibility here.
Okay. Thank you. So basically, you don't expect, that you need to retrain the model very often. Maybe it's possible, but it seems like, it doesn't affect too much, correct?
Yeah.
Okay.
And also the training cost is actually not that large. Like it's 6 hours to train the model. So even if you want to train it like frequently, I don't think it is a problem.
Okay, we have a question in the room.
Yeah. So Hamas, University of Iowa. So one of the problems that Tor faces right now is that there's 3 hops between the client and the end website, which makes the packet travel a lot more distant than it's supposed to. So it increases the latency that the packet takes from the client to the end server. So now that the packets are somewhat delayed in some instances, do you have an idea of what the increase in latency might be and how it might affect how users go away from Tor or how they might still use it?
So the latency is one main factor we need to consider when design a defense. And in our case, we measure the overhead, and it increased about 16 to 18% on average. So I don't think it's a large time overhead if we consider it is an effective defense. And also, we have actually another hyperparameter in the defense, which controls that the maximum delay you will have every time you send out a burst. Yeah, and if you're very sensitive to the time overhead, actually for the user, he can choose to set it to a low value so that you will get a response in a shorter time period. Yeah, so that you can reduce the time overhead further.
And also, was this evaluated over just 2 geographic locations? So I imagine it's Hong Kong and the US. Did you try it over different geographic locations, for example, longer distances, and that might increase the latency that you would see?
Unfortunately, no.
Okay, thank you.
Yeah, thank you.
Okay, so let's thank the speaker again.